Hello, everybody. Welcome to today's lecture. Um, so today we're going to talk about 2.5, which is measures of the center of the data. Last time we talked about measures of the location of the data. So we talked about quartiles, percentiles. Now we specifically want to talk about the center of the data. It's typically a very important topic. We want to know what is the middle of our data set, and what exactly do we mean by middle? Do we mean exactly the middle, or do we mean more of a weighted middle? These are words that we use like average, right? Like the average person does this, or the average test score was this. These are all measures of the location or the center of the data. We already talked about one last time, which was median. Let's remember what that is real quick. So let's start with the section title here, measures of the center. Come on. Measures of the center of the data. And this is 2.5. Okay, so we're skipping 2.4. So we already saw median, right? Median is the exact middle. In 2.6, we're going to look at why these numbers aren't always the same. But when I'm looking for like when I'm looking at test scores, for example, I'm often looking for the median. I'm not looking for the mean or the average. And that's because the median is less influenced by the extremes, meaning the lowest and the highest scores. Whereas the mean is it's very influenced by the extremes. It's if there's a lot of scores towards the bottom, namely if there's outliers towards the bottom, it's going to drag down the mean. And if there's outliers towards the top, it's going to drag up the mean. For example, income, that's another example where median is more useful than mean, because with income, there's a lot of outliers in the upper extremes. There's a lot of people who have way more money than the average person, right? Namely, like billionaires. A billion is a lot of money. The number a billion, I think we often kind of just think of it as a big number up there with a million, but a million and a billion are very far away. Okay, just to give you a perspective, a million seconds takes about 11 days. I don't know. I might be a little off on the numbers here, but uh, in general, a million seconds is somewhere around 11 days. A billion seconds is about 33 years. Okay. That's a huge difference. So when you have people who are billionaires, it's dragging the average income up considerably because they're so far away from even millionaires, right? Um, the so when you're talking about income, median is often more useful because it's less influenced by those upper extremes. It gives you a better picture of what the average everyday person is earning, right? Just like with test scores, if I have a bunch of people who didn't take the test and so they get zeros, they're going to drag down the average a lot because those are outliers towards the bottom. Whereas median is going to give me a better example of what the average student, how the average student did on the exam. Okay. So that's why that's why we even have different measures in the first place. So we've seen median in the last chapter, the exact middle of the data set. The mean is what we typically think of as average. Okay. Average technically can mean a bunch of things. It could mean the mean or the median, but we typically use it interchangeably with mean. Okay. There's not really an actual definition of this, but to find it, what we would do is we would add data values and then divide by the number of data values, which we've already seen, right? So if we want to define the average of the 10 test scores, we add the 10 test scores together and then divide by 10 because there were 10 of them. Okay. So the mean is a little more weighted than the median is. The median is just your exact middle, whereas the mean is influenced a lot more by the outliers. So when we're talking about the average of something, we should really be more precise than that. Are we talking about the mean, or are we talking about the median, or are we talking about a third one called the mode? Okay, the mode is the most frequent data value. Okay, the most frequent data value. Now, if we're thinking about this in terms of like test scores, this doesn't seem very useful because we might not even have a most frequent data value, right? We might have like all different data values. Or maybe we just have like two 100s and then everything else is different. So then the mode is 100. That doesn't really give us a good picture of what the average person did. Technically speaking, the mode is the number which, if we were to pick a number out from a number out of the data values at random, it's the one we'd have the highest probability of picking. So that would be the one that's most frequent. Now, where would this be useful? Well, this would be useful if we have non-quantitative data, namely qualitative data. Okay. This is useful for qualitative data. If I'm doing a survey of everybody's favorite color, right? So if we have blue, and let's say that 10 people picked blue, okay, and then we have red, and we have 5 people who picked that. Purple with 7 people. Green with 3 people. If I want to talk about the average favorite color, it's kind of a weird way to state it, but that is something we want to know. What is the most common favorite color? Namely, if I picked a person at random and I wanted to guess their favorite color, which one should I guess? What do I have the best odds with? The answer would be blue here, right? And that's just because it occurs the most frequently. So it's what's called the mode. So when we're talking about qualitative data, if we want to talk about the average, we typically want to talk about the mode, which is the one that occurs most frequently. With quantitative data, we typically want to pick one of the other two because the most frequent one, it has much less chance of occurring because usually we have a lot more options. Like if we have test scores, you can get anything from 0 to 100. So there's less chance that a lot of them are going to overlap in the first place. Okay. So let's talk about mean a little bit more carefully because, I mean, like I said, we use that interchangeably with average a lot. So obviously it seems like it's the most important and most used one. So let's dive a little bit deeper into it. So let's go with mean. Let's first look at the notation. Okay. So first, there's the sample mean. and the population mean. Okay. The differences here are just where they come from. The sample mean is the mean of your sample. The population mean is the mean of your population. So if we're talking about the average height of people in America, the population mean would be the average height of every single person in America, whereas your sample mean would be the average height of the group of people that you studied. Because you can't, you're not typically going to be studying every single person in America, right? You're going to take a sample of America and you're going to look at the average height there. So if we're talking about the sample mean, we usually represent average with X with a little bar over it. Okay. Which is read as X bar. Okay. So X bar is the sample mean. For the population mean, remember before I said for population variables, we typically use Greek letters. Here we use the Greek letter mu. Okay. Written as mu. So it's a little easier to see it typed. If you look at your book in section 2.5, it has it right there. And it has the pronunciation of it as mu, M-E-W, but it's actually written as mu in for the Greek letter. So typically we're using X bar in order to estimate mu, right? That's what we're typically doing. We're taking our sample and using it to estimate something about the population. So we take our sample mean and we want that to be close to the population mean. Okay. Trying to see where it's written here. I'm kind of skipping around, so I want to point you in the right direction here. So it talks later on about the mean of the frequency table and about the notation for that. I want to be a little bit more general. For the sample mean, the formula, we already know how to find it, right? We add them all up and divide by however many there are. But how do we write that with the standard notation? Okay. So let's say the formula with standard notation. So it's going to look a little weird at first, probably, but I'll explain it. So X bar is equal to, well, we want to add them all up, all of our data values up. Okay. The way we write adding things up is with this Greek letter sigma. Actually, I can write this even better. Okay, sigma. And there's a couple ways we could write this. A lot of times we just write it as sigma x, where x is our data values. Okay, so all this is saying in English is add up your x's, namely your data values. Which we already know that's what we're supposed to do, right? We add all of our data values up, and then we divide by however many there are. If you remember a couple of lectures ago, we said that the number of things in a sample is represented by a lowercase n. Okay. So this is how we would write it in standard notation. Now, sometimes we like to index the data values, like we would call them x1, x2, x3, x4, x5, etc. So that we can distinguish between them. In that case, if we so this is the case where we don't have any indexes, we're just kind of throwing them all together. If we actually order them and want to distinguish between them, we would do something similar. We would add up, what we'd say xi, where I is a subscript here, and we would do it from I equals 1 to n. Okay. So the bottom number here tells you where to start. The top number here tells you where to end. So you start when I equals 1. You end when I equals n. We don't have to write the I equals the second time. As long as you write it the first time, it's implied. So if you have your data values like your test scores, right? Like, I don't remember exactly what they were. I'll just write a few of them also. I think these were the first 5, but I could be wrong. This first one would be like x1. The second one would be x2. The third one is x3. The fourth one is x4. Fifth one is x5. Okay. So notice there's 5 of them. So the last one is the fifth one. So that's why we're using n here, right? These are all the same n. However many you have is also going to be the last one. So this is literally just giving them names like 1, 2, 3, 4, 5, but we want to have a variable there too, so we know that it's not, like we're not just calling the number 0, 1, so we use that x there to kind of differentiate them. So we're calling 0, x1, 41, x2, etc. We're just saying what place in our data set is this number. 66 is in the 4th place, so we'll call it x4. So that's what the notation here means. It means the sigma means add them up. The subscript I is getting replaced by these numbers every time, right? This tells you which number to start at, 1. So if we wanted to start at 3 instead, we would start at I equals 3. And then this tells you where to end. In general, it's going to be n, but you could also just replace it with a number if you know where you're going to start. Like you could just replace it with 5. So this is the notation here. Let me actually, I can do this, where I can, I don't want to move it, I want to copy it. I can transform this to math. So, whoop, that didn't work. Here you go. So this is what it looks like with math. And let me try to make this, I don't know how to make it bigger. Well, either way, I'll just delete that. But you can see it on the side here. This is what it would look like. You have this Greek letter sigma. This is a capital sigma, by the way. There's a lowercase sigma, which we'll use in a little bit. But we have the capital sigma x divided by n. Or you have it like this. Sometimes it's written on the side like this. Sometimes it's written underneath like I wrote it. It doesn't really matter. So this is what it would look like. Like this is what it would look like in your textbook typically. It doesn't actually use this notation in this chapter, but this is the notation it'll be using later. Okay, so I figure we might as well just start using it now. Just as a reminder, the sample mean is what's called a statistic. Just a reminder of these earlier definitions, right? Because a statistic is any number we take from a sample. And the population mean is called a parameter. The parameter is any number that we take from, that we calculate from a population. And the statistic is any number we calculate from a sample, okay? So just getting used to the notation here, right? Might as well go ahead and delete all of this because we don't really need it a second time. How do we write it with a population mean? So mu, well, it's not too much different. Okay, mu, so you either index the x's or you don't. If you don't, you just write it like this. Your population is still the same, but like your data values are still the same, but you have a different number of them now, right? Because you have the whole population. You don't have this lowercase n. That tells you how much is in your sample. For a population, we typically use uppercase N, or we call it big N and the other one little n. And if you prefer to index them, you can do I equals 1 to n of xi's divided by big N. So the only thing that changes is just we use a capital N for population typically, and we use a lowercase n for sample, just to indicate that the population is typically bigger than the sample by definition. So it's pretty much the same thing. We'll actually start using this notation. The book uses it in 2.7, so it's not really that far away, so it's good to look at it now. All right, what about the median? Is there a formula for the median? Okay. The notation for the median, it's not always standardized, but typically we just use a capital M. And we don't typically talk about population median versus sample median. Usually we're just using it in the context of a sample. So we don't really have a different version of it for population. But we usually use the letter M for it. So we don't have a formula for median, but we can find a formula for the location of the median. Meaning, like, if your data is in order, where exactly is your median going to be? Okay, so the location of the median is given by the formula n plus 1 divided by 2. Okay. So if you have 10 points of data like we did yesterday, you put that in here, you get 11 divided by 2, which is 5.5. So that kind of goes back to what we were doing with the percentiles, where you round down and you round up and then take the average of them. So if we get 5.5, we take the 5th and the 6th data value and we average them. If we had 21 points of data, for example, if we plug that in, we get 21 plus 1 is 22, divided by 2 is 11. So we just go to the 11th data value, and that would be our median. Okay. This formula isn't really necessary because a lot of times you can just take your data and count inwards until you get to the median. But this would be helpful if you have a very large data set, right? If you have 100 data points and you want to find the median, it could take a while to count. So instead, you can say, okay, well, I have 100 data points, so 101 divided by 2 is 50.5. So it's a tie between 50 and 51. So I find those data values and average them. Okay. We'll encounter some of this later when we're finding the median. So, and we already did some examples of it in the last chapter. It's not any different. So I won't do another one right now. I think the only other thing I want to mention from this chapter, and I'm not going to write it down, I just want to verbally say it, because there's it writes it down in your book, and it's not really going to be important to us like in terms of using it. It's more like the theory behind this. Why are we able to use the sample mean or the sample whatever, sample statistics, in order to estimate what the parameters are? So why are we able to take the sample average and use that to make statements about the population average? Well, we can't always do that. There's something special called the law of large numbers. Okay, the law of large numbers, and the book states it particularly when talking about the mean, right? Which is what the law of large numbers is typically talking about. The law of large numbers says that if you take samples of larger and larger size from the population, then the mean of the sample, your x bar, is very likely to get closer and closer to your mu. Okay. So in other words, the bigger your sample, the closer X bar will probably be to mu. And I say probably in terms of like probability. There's a high probability that X bar will be close to mu if your sample is large. So as your sample gets closer to your population size, X bar will likely get closer to mu. So that's why it's so important for us to have a big sample size here. Because the bigger the sample size is, the more likely it is that the sample statistic will be close to the population parameter. Okay. So we can make these estimations. We can estimate the population mean using the sample mean, but it's only really justified as long as we're using large samples, meaning your sample is close to your population mean. And even then, it's still only giving us a high probability. Okay. We'll look exactly like when we can make those claims later and with what probability. Okay. 2.6 is really short. 2.6 talks about skewness and how it affects the median and the mean and the mode, but we're mostly going to look at the median and the mean. Okay. Let's see. Let's first define what skewness means. Right? What do we mean when we say our data is skewed to the right or skewed to the left? Well, we mean that it's more concentrated on one side than it is the other. Right? If it's not skewed, then it looks completely even. Okay. So, for example, if we have data that looks like this, then this isn't really skewed, right? Most of it is concentrated in the middle, and then it's symmetrical on both sides, right? So if our data is symmetrical, it is not skewed at all. Now, how often do we really get perfectly symmetrical data? Well, not really often, right? The book gives an example with a bar graph instead of this, which might be a little more useful. So we have something like this. Right. So the left and right sides of the center, they look exactly the same, or they should. I didn't draw it perfectly. But this is symmetrical data along the center, right? So here it's not skewed at all. In this case, the mean and median are the same. Okay. So let's say I have some data where well, let's do one example where it looks like this. Okay. Here our data is perfectly spaced apart, right? 10, 20, 30, 40, 50. They're all exactly 10 apart. When we find the median, if we just start on the sides and count in, right, we have 50 and 10, 40 and 20, 30. So 30 is our median. If we find the mean, we do 10 plus 20 plus 30 plus 40 plus 50 divided by 5. Okay. So we have 90, 120, 140, 150 over 5, which is 30. Okay. So here our data is perfectly symmetrical because it's spaced perfectly apart. So the mean and the median are the exact same. What if we have something like 10, 25, 45, 65, 80. Is this data symmetric? Well, let's look at the space between them, right? Here, there's 15, they're 15 apart. Here, they're 20 apart. Here, they're 20 apart. Here, they're 15 apart. So it is symmetric, right? It looks identical on both sides. It's evenly spaced. The median here, again, is just the middle number, which is 45. And then the mean, I'll just throw it in the calculator just to confirm that it's 45 here. We got 10 plus 25 plus 45 plus 65 plus 80 is 225. And then divide that by 5 and we get 45. Okay, so it works here. We saw, if we go back to 2.3 here, right here with this data, which you can't see all of. Okay, so we have these test scores. They're not at all symmetrical, right? This is 41 apart, 9 apart, 3 apart, 13, 2, and then on the other side we have 7, 5, 9, 5 apart. Very different. Skewed very much to the left because there's a lot more space between 0 and 41 than there is anything else. So because of that, our mean and median aren't the same at all. In fact, the mean got dragged down. Okay, so when our data is skewed to the left, it's going to drag the mean down lower than the median. Okay, so if our data is skewed to the left, so if it looks something like this or something like that, right? Okay, so we have a bar graph here. So there's more data is concentrated on the left, or if we look at it with the numbers, right, 0, 41. These aren't the exact same again, but something like this. Well, here they're 41 apart. Here they are 14 apart. Here they're 8 apart. Here they are 3 apart. The distance apart is way more concentrated on the left side. So with this data, the median is 55. What is the mean? I'll just put in a calculator again. 0 plus 41 plus 55 plus 63 plus 66 is 225. Divided by 5 is 45. So the mean is lower than the median. So the mean got dragged down lower, but the median stayed exactly the same, right? It's always going to be the middle. So when we have more outliers or more extremes on either end, the mean is going to be pulled towards those extremes, whereas the median isn't influenced by that. It's just always going to be your exact middle. So the median is it's not really influenced by those extremes like the mean is. So if our data is skewed to the left, and remember, typically we're ordering this smallest to largest, so that means that there's more small values than there are large values. Okay. Mean is lower than median. If it's skewed to the right, so there's more large values than small values, it's the opposite. The mean is going to be bigger than the median. Okay. We'll have this opposite effect that we have on this one. And we already saw if they're not skewed at all, the mean and the median are equal, right? So these are the three cases. Skewed to the left, mean is smaller. Skewed to the right, mean is bigger. Not skewed, they're equal. Okay. So this is just a good way to gauge immediately, if you see your data is skewed, which one you should use, the mean or the median. Maybe you still want to use the mean, but maybe it's also helpful to look at the median so that you have a comparison and to get a good check of making sure your numbers are right. Right? If your data skewed to the left, you're expecting the mean to be lower. If it's not lower, you know you did something wrong. Okay. Let's see where we are in time here. 35. Okay. Doing really good. I think the next section is pretty large, so I think I'll put it in its own video. So I will I'll see you guys for that one. So thank you for watching this, and I'll see you then.